Hello, we are Team 1060 from Texas A&M University, coached by Dr. Kang, and this is our submission for Problem B of SCUDEM 2025, an AI Ouroboros. When we examine the modern AI industry, we notice a couple things. Modern advanced AI models can now search and access the internet. This is coming at a time where the content on the internet is becoming increasingly AI generated in the form of articles, videos, and images. On top of this, we see that AI agents are also specializing into various roles. We have AI agents that are really good at language models, and other AI agents that are very good at image generation, for example. At the same time, training these advanced AI models require more and more training data. This leads to a paradigm where new AIs are going to inevitably use content generated by other AI models to have enough training data to be able to create something. This is important because using data from previous generations of an AI model can mean less initial data is required. Overall, our goal is to examine the impact of human input, as in human-generated content, recursive training, and also parallel training on AI development. We intend to do this by examining several AI models training at the same time. Historically, AI training has occurred with completely human-made data. However, recursive training has been explored recently because it can create more advanced AI models with less initial data. In a lot of cases, multiple AI models are being trained at the same time. We want to examine what happens when multiple AI models are training off of the outputs of other AI models. Now we're going to talk about how we implemented these concepts within our model. We're depicting training of an AI by changing an accuracy value A. A depicts the proportion of AI outputs that are acceptable. Each AI model has an associated accuracy value, and the human input also has an associated accuracy value. We implemented recursive training within our model by using the value R sub n. Additionally, we also used the growth factor alpha to weigh past generations of a certain AI model. R sub n is the average accuracy of past generations of an AI weighted by the growth rate alpha. We use an alpha equals 2 as a growth factor for our models, which means that some generation of a past AI model has double the weight on the training of a new AI model compared to the generation immediately before it. This value R sub n is computed for every single AI within our model. The training of an AI within our model are affected by several different sources. Each input source contributes in a different proportion to AI training, so several proportionality constants are used to change their effects. The first proportionality constant is pH, or the proportion of training data that was from human input versus all other AIs. Proportionality constant PS determines the proportion of AI source data that is from older generations of the same AI. 1 minus that value is the proportion of AI source data that is from older generations of other AIs. In order to scale the AI source training data correctly, a factor of 1 minus pH must be applied. When more than 2 AIs are present, other AI source training data is weighed equally. For example, here we have a basic 2 AI model. Adding a third AI means that we weigh the second and third AI equally to train AI number 1. This is represented by the other factor O sub n, the average accuracy values of past generations of other AIs. O sub n is simply the average value of the recursive factor of the other AIs. Whenever O needs to be computed, the R value for every AI is computed.
Each cycle of AI training will cause data to degrade, straying further from the ideal human input. Seen below, we can say that the accuracy for AI1 in the next cycle will depend on human input and the accuracy of it, AIs running in parallel and the accuracy of their input, and the recursive factor of AI1 and its accuracy. R represents our degradation constant, and it is found based on the assumption that the output of an AI will never be better than its inputs. With that assumption, we can say that the accuracy of AI1 in the next cycle will be a fraction of the total data accuracy, human and synthetic, caused by degradation. These are the assumptions used in our model. The growth rate of AI, represented by alpha, is constant. People will always add content to AI datasets at a rate proportional to the amount of data the AIs will add. This is the constant human factor. People generate content uniformly across AI datasets. Human accuracy is constant and not affected by any factors. AI outputs will always be less accurate than their inputs, and this is degradation.
As the number of AIs increases, there's actually not significant difference in the accuracy of the dataset after a certain amount of time passes. In this one, we have no specialization, but regardless, the number of AIs, once it passes 2, because of our constraints of having identical AIs, does not affect the accuracy rate. The degradation constant, which is how much each iteration the AI will kind of make mistakes or kind of corrupt the data, as that ratio becomes greater between simulations, accuracy that it approaches as iterations increase decreases in a roughly linear fashion. As the proportion of human data added to the dataset increases, the equilibrium point increases, as shown in the graph on the right, as well as on the left, where as we go from blue, orange, green, and the proportion increases, the accuracy also increases, reaching up to notably 0.9, which is 1 minus r. So as it specializes, or as the p sub s increases, we see here in a roughly linear fashion, the accuracy also increases from 0.6 to 0.8 for these specific constants. Now, we have a relationship of human input into the datasets and the proportion of specialization here. If we see here, first of all, as the proportion of human-generated data increases, regardless of the proportion of specialization, the accuracy does increase. But if it's more specialized, we see that it creates this red curve rather than a linear curve. So if we have higher specialization, then we can get away with having a lower human input and still get the same amount of accuracy in the end. But of course, we also do have R, which as R increases from 0.1 to 0.2 and then to 0.5, we see that it flattens out. So R is also involved here. Okay, so here's some limitations of our model. Human inputs are often affected by AI content, and this is not shown in our model. The proportion of training from other AI datasets is unequal. Real datasets vary in distribution, different size, content, etc. Human input can change in proportion between different AI datasets. AI training involves a feedback mechanism. Our model assumes AI has no feedback regarding its outputs, like how accurate it might be. Datasets are of different types, images, articles, etc. Our model assumes that AI training involving these different types are all weighted equally. Different AI models are not identical in reality, but that is what our model assumes. So our testing assumed that all datasets had the same proportion of human input as well as identical degradation rates. There is more to quality of output than just right and wrong, but that is not shown in our model. Our conclusion, an AI model is less prone to collapse if it uses more of its own data rather than other AI data, if it uses its own dataset, including the people's data. AI models will reach equilibrium rather than collapse in the long run if people add to the datasets. In our model, the quality declines before slowing down and reaching an asymptote. Similar to the last point, it will reach an equilibrium and it will go fast before slowing down.